Okay, hello everyone. This is nice, our nice cozy little hideaway spot here in the dark. My name is Steve Gallant. I'm the founder of MultiModel Research. We do free text and machine learning. So we're going to, this is touted as an introductory talk, but I'd like to bring some more advanced things into it also. So we're going to try and cover a lot of bases in a limited amount of time here. We're going to talk about applications for text and predictive modeling. There's a wide variety. Look at the difficulties in this whole operation. It's not so easy to deal with text and predictive models. Then for the kinds of approaches I want to give some motivation for those from a neural net point of view and from computational point of view. And then just dip our collective toes into some of the current approaches. We're not going to be able to get into details here. I'll try and do a live demo of classification using some of these techniques and then talk about current work. So in terms of applications, one application is if you're a Bloomberg or a Thomson Reuters, you've got 1 million stories a day coming across your news wires. Your subscribers only want to see stories about oil or gold or something like that. They don't want to see 1 million stories a day. So what that means is you have to have a list of set categories, typically several thousand, where for each story you have to put whichever of those several thousand tags apply to that story onto that story. And then it makes it very easy for the subscribers that only want to see stories about gold. You just give them the stories that have gold as a tag. But putting those tags on is a lot of work, right? Several thousand tags for each of 1 million stories a day. So this is something that's good to be able to automate as much as possible. Another example for text and machine learning is the electronic health record. There's a lot of free text in the electronic health record. There's doctor's notes, nurses' notes, discharge summaries. This is actually primary material. It's not secondary. Next time you go to a doctor, you notice they type in all this stuff, and they go back and they check those pesky boxes for whichever things apply. The pesky boxes are the structured data. The free text is the primary unstructured data. So the more that we can deal with that automatically, the more we'll be able to predict things operationally and assign medical codes and that sort of thing. Another example for use of free text in modeling is for marketing. For example, if you have call center notes, you may want to have some models that predict when a customer is likely to churn, including the call center notes, which is pretty valuable stuff, right? That's your person speaking directly to the customer. So again, this would be something that would be good to be able to work into our predictive models and see who's going to churn. Another example is financial. There's already a number of hedge funds and so on that look at sentiment analysis when they are making their decisions. Content providers need smart search. So in particular, if you take a big document and you paste it into your Google browser, it's going to say, can't do this, because it's set up so that it only does not that long text. Now this is something they could do with it. They do it for efficiency. But being able to understand language better for the search process is important. I'll come to an example of that. So language is hard. Here's my favorite example from Groucho Marx. Time flies like an arrow, food flies like a banana. Okay? So these little words like make a big difference with what's going on. So language is just all around nasty, but it's something that we do without thinking very easily. If you're trying to build marketing models, we're used to using structured data, where you have a database and you've got different columns for age, income, and so on. There, everybody already knows how to build predictive models using that kind of data. But how do you do it with text? Text has variable length, the structure of text is important. Apple is better than Android versus Android is better than Apple. Has the same words, but it has a very different meaning. So one of the main things I'd like to, main points I'd like to make here is that representation is kind of an important thing, and it's different than machine learning, and it affects any kind of machine learning that you're going to be doing. And here's my favorite example. We can represent integers just by hash marks. So if we want to do 18 times 7, we can represent the problem this way. And there are ways to do it, doing hash marks. But it's a lot easier using decimal in terms of how efficiently we can do these computations. So representation is important, different than machine learning. So what's a good representation for language? Also, by the way, a separate interesting topic is how the brains do it, right? We do it all the time without thinking. Well, something's going on there. How in the world are we able to process this language at all that we do so naturally and automatically? So one of our main goals is to find a representation that's good for text with respect to machine learning. So here is our one neural motivation slide. Here we've got a little brain on a slide, and we're representing the neurons as either firing or not firing. Of course, this is a very simplified, abstract representation. And if we wanted to turn that into a vector representation, we could just look at these neurons and line them up in some arbitrary order, and then we can have sort of the state of the brain represented as a fixed-length vector, where you have one component for every neuron. I hope people, vector is just a list of numbers with some operations. Okay. So that's the basic correspondence, both in neural modeling and that we're going to be using in a way, is that a vector component corresponds to a neuron activation. That's the neural motivation only. That doesn't solve any of our problems, right? So the computational motivation is that in order to build our machine learning models, almost all of them take as inputs fixed-length vectors. Vectors of fixed length. Okay, all the favorite ones you find around the house, support vector machines, whatever. So we want to see if we can represent language, for example, a news story, as a fixed-length vector. Okay, not so easy to do right out of the box, right? Because it have all kinds of different lengths, and here we're trying to represent it as a fixed-length vector. Plus, there's structure involved. So in order to even make a start, we can say some things about how this vector is going to have to look and how it's going to have to work. One important thing is that we're going to need to use a distributed representation. So we're going to need to be looking at the patterns over the vector and not the individual components of the vector. We have a thousand-dimensional vector. There's no way we could represent all of the words, for example, in any sort of reasonably sized corpus of documents. But if we look at the patterns, where the pattern is over all or most of the components in the vector, that's a huge representational space. It's like exponential in the size of the vector. So that gives us enough elbow room so we have a fighting chance to even just be able to represent the words. Not to mention what we really want to do is to represent the words and the structure in this fixed length vector. So we have to use patterns, we have to use a distributed representation. So how are we going to do that? I'd like to motivate that with, well, the key thing behind that, there's this, that vector sums preserve recognition of terms. So this is counterintuitive. If I tell you, I take 5 numbers and I add them up and I get 37, you can't tell me whether 15 was one of those numbers, right? There's not enough information. But you can do that, surprisingly, for high-dimensional vectors. So here we have sort of an initial representation where for each word, we're taking a random +1 - 1 vector. And then we're taking some subset of these words and adding them up in order to get this vector V. Okay, so the thing that's a little counterintuitive is that from V, we can tell which vectors were in that sum very efficiently. And the way to do that is if we take each vector and we take a dot product with the thing we're trying to figure out whether it's in the sum. If it has a high dot product, then it's very likely that it was in the sum. If it has a not high dot product, then it's very likely that it's not in the sum. Now this is noisy. You have to worry about the capacity of the vector. The longer the vector, the surer you are. There's always room for error, and so on. But when we take the dot product, what I mean by dot product is we multiply the corresponding component. -1 times 0, 1 times 2, and so on, and add them up. That gives us the dot products. And if we now, this says that Smart and Banker were in the vector, and in fact this vector B should be the sum of Smart and Banker. So that's by way of motivation, is that superposition or addition of high-dimensional vectors. The resulting vector gives you a lot of information about what the composing vectors were. So there's more to the story. So in this simple example, we just took random vectors for each word, and that at least showed that you could represent a document, by just adding up the words in the document. But we need to do better than that. For example, we want to have doctor and physician have similar vectors. And the reason for that is that suppose in our training data it only uses the word doctor, and now we want to go and apply it, and we run into a document that uses the term physician. Out of the box, we've never seen physician before, so we're lost, and we can't do anything to that vector. We just throw it away or treat it as zeros. But if the original vectors are formed so that the vector for doctor is similar to the vector for physician, then this unseen training data will be able to handle the right way, because it would be as if doctor were there rather than physician. And we've seen a bunch of training examples that have doctor. So it's very important for modeling to be able to get similar words, have similar vectors. And there's a lot of ways to do this in the literature. Word2Vec from Google is probably one that's best known. There's these glove vectors, which is Socher and Manning and someone else from Stanford, which I would recommend. We've gotten better results with glove vectors than Word2Vec. And it's its own sort of cottage industry, is creating these vectors from unlabeled text. We'll go over Wikipedia and a huge amount of text. It's a lot of work, but you only have to do it once, and then you can use it from then on. The other way of getting the representation is to do it by deep learning approach, where if you have a problem and you're training a network, the sort of last thing you train at the bottom layer is the representation for the words. This is a second way of doing it. But you notice in the example I gave where there's only doctor in the training data, but the test data, the applied data has physician, it's not going to work for that because it will only be able to train things that it's seen before. Okay, so with this as background, I'd like to give a little bit more background. This was stuff that I did an astonishing 20 years ago. So this is a document retrieval system based on some of these techniques, and this was at HNC. So the way you can build a simple document retrieval system is that the word, you get the vectors for the word. We just talked about a couple ways to do that, Word2Vec and glove. Then the document is just the sum of the vectors for those words that are in the document. Okay? So if we're doing 500-dimensional vectors, each word is a 500-dimensional vector. For this document, you see which words are in the vector. You add up the vectors for all the words that are in that document, and you end up with a single vector for the document. And then you can do the same thing for a query. You see which words are in the query. This is for document retrieval, where we're going to find the closest document, get its vector in the same way. So these high-dimensional vectors, you can think of each vector as a direction in high-dimensional space. So each document has a direction, and each query and a query will also have a direction. So document retrieval consists of finding the documents with the closest direction to the query vector. So there's a lot of details that I'm not going to go over here, but that's basically all you need to get a document retrieval system. And here's a picture of adding up the word vectors in order to get the document. Okay, so there's some stuff missing from this. So far, we haven't done any structure, right? So if let's say Apple's better than Android, that document will have exactly the same vector as Android is better than Apple. There's no structure. And we want to be able to put structure in, including if, here's an example, the smart banker saw the Indian elephant versus the smart elephant saw the Indian banker. So this is an example of the importance of what's called binding, where in the first sentence, smart modifies banker, it doesn't modify elephant. Okay? So we need to get that structure in for some things, like if we want to try and do machine translation with this would absolutely be necessary. So we want to be able to represent arbitrary sentence structures for some things, for example, machine translation, including nested embedded clauses of different types. So how can we do this? Is there a way to do this so that we still have a nice distributed vector with our same fixed dimensionality? So we want to be able to represent not only the words, but also the structure without expanding the vector. So how can we do that? There's a couple of different approaches, families of approaches. One is sort of a representation-based approach. The other, which is sort of a bottom-up approach. The other is top-down approach, which is deep learning. So the representation approach is bottom-up constructive. And I'm going to briefly talk about those. So for representation approach, the focus is the idea. Here's the idea: if we can easily get one of these vectors for what we're trying to represent, then the learning is easy. We can use ridge regression, regular regression, support vector machines, or so on. That makes the learning problem very easy if we can get what we want to represent as a single fixed length vector. We can use simple training methods. So there's two basic ways of doing this. One is vector quantization approaches, which people at Stanford have some very good papers on. The other are vector symbolic approach architectures, which has, well, they both have history, since the vector quantization comes from image work, which also has a history. The advantages of the bottom-up representation approach is learning is very easy and simple and fast. It's not going to take days or weeks to train your model. You're going to take, minutes or an hour on a single CPU. And it's easier to handle full-size documents. If you want to be able to handle large news stories, the bottom-up representation approach is much easier to work with. The performance can be better if there's not enough data. Okay, I'm sorry, if there's not a huge amount of data, is what I'd like to say. But on the case where you do have a huge amount of data, the deep learning methods currently produce better results. So if you're trying to get the very best results on a data set, you're probably going to get better results using a deep learning approach once you get your neural net to converge and that sort of thing. Okay, so these are the two bottom-up approaches: vector quantization. So the basic idea that Coates and Ng have is to represent something. It's actually easier if I speak in terms of images. You can take little patches of the image and take a collection of those, and that becomes a coding dictionary, so that now if you have a new image, you take each member of the dictionary. If you look at it versus a patch in the new or old image, you can get a similarity with that saved member of the coding dictionary. What it's doing is it's taking this image and it's converting it to a fixed length vector, is basically what it's doing, where the components are how well each dictionary member corresponds to this particular thing that you're looking at. I'm sorry I'm being so sketchy here, but I don't really have time to go into this in detail. Here's another thing I can just sort of give you the key intuition, but without going into the detail. This is, on the vector symbolic side, a way to code structure, for example, with sentences. Suppose you want to code the smart Brazilian banker saw an Indian elephant. We need to bind smart Brazilian and banker, smart and Brazilian to banker. Okay. So an easy way to do that is to have a matrix for each type of binding. For example, here's a matrix for actor, a matrix for verb, a matrix for object. These are matrices that are done at system generation time and fixed, and they can be random matrices. Okay? So now we're taking the sum of the vectors for this phrase, smart Brazilian banker, multiplying it by this square matrix. You end up with a single vector. But you can show that that encodes that Brazilian is going to be associated with banker, whereas for the object, Indian is going to be associated with elephant, because we're multiplying it by a different matrix. So multiplying it by a matrix casts it into its own high-dimensional space to keep things separate. And that's the trick for doing binding using this approach. And you can show that similar structures get mapped into similar vectors doing this. That's another key thing for learning. Just like you want similar words to have similar vectors. Okay, so that's a quick look at multi-classification. So I'd like to do a demo here. All right, so okay, so this is a demo that's on our website here. And this is a classification demo. Remember I said one of the applications is taking news stories and putting tags on it. And this demo is sort of a scaled down version. It's only 500 tags to do that. So we can take a news source, for example, Financial Times, and pick a story. Anybody have a favorite story on here? This is today's. Let's do the headline story, for example. Okay, and paste it into our demo box. All right, this is kind of short, but you can do all of this. Hit classify, and this is politics and government news. This is actually not this one it didn't do a great job, although I guess it's Greek politics. But you get the idea that this is able to do it very fast. It's able for each of these topics that it classifies. It's able to see which are the words that are most strongly associated with that topic. you could never do this by hand coding a bunch of rules. Okay, you would never know all of the words that apply to each of these large number of topics. You can play around with this on our website. Okay, so let's come back here. All right, so here was an example I did yesterday, in case we weren't able to do it live. All right, so those are the constructive bottom-up approaches. Deep learning is the current rage, and I wanted to just give a quick kind of intuitive introduction for that. This sort of interest started, the recent revival of interest started with Socher and so on. Of course, Jan LeCun has been doing these sorts of things for a while with images, zip codes, and that sort of thing. So the advantage of the deep learning approach is you usually get better results when there is a lot of data. If you don't have a lot of data, sometimes you get better results with the constructive approach. So that's the thing to keep in mind. But if you have a lot of data, you're trying to win the competition, you're probably better off using a deep learning approach. The other way of looking at it is with deep learning, you have a lot of trainable parameters. It allows you to use more data in order to build a more complex model without overfitting. So the more data, the more complex model you can have without overfitting. That's a general thing that's going on. Disadvantages is training is usually slow. It requires neural net craftsmanship. Okay, you have to worry about the network not converging. All kinds of things. You have to tune a lot of parameters. You have to have a lot of data. And it's harder to do large-size documents using deep learning approach. For example, full news stories. And this is just a picture. This is actually sort of an image processing picture, just to give. This is kind of a typical picture stolen from one of LeCun's talks. And you've got multi-layers and so on. There's this notion of pooling, where you do dimensionality reduction by combining parts of vectors across things. Okay, so in terms of what we're looking at now, we're looking at positional binding, trying to encode not only the structure and the objects within a fixed dimensional vector, but also the location. So this is important for image work, because if you have something at one point in the image, arguably that's important. Okay, you need to represent the location one way or the other. We're working on a paper on that. Another thing we're working on is medical text, being able to make predictions from the patient record, and also being able to automatically put medical codes in the record. It's kind of a big classification point. All right, so before we get to questions, the takeaways: representation is important. It's possible and advantageous to represent text by fixed length vectors for building models. And then there's this trade-off of best performance possible with deep learning versus training speed, ease of training, and ability to handle large documents with some of the constructive bottom-up approaches. So, okay, I'd be happy to have any questions.